There we go. Okay. So if you have a sequence an and a number L, we say that that sequence converges to L if, for every epsilon bigger than 0, there exists a big N such that for all little n bigger than big N, absolute value of a sub n minus L is less than epsilon. And similar, like we have all these other definitions of limit points and limits of functions and continuity. We say that a point is a limit point of some set U if, for every delta bigger than 0, there exists some U in U such that 0 is less than absolute value of U minus P, so U is different from P, but it's within a delta neighborhood. A point P is isolated in U if P is not a limit point, or equivalently, if there exists a delta bigger than 0 such that for all U in U different from P, absolute value of U minus P is bigger than or equal to delta. For a function defined on some domain U and a limit point of U and a number L, we say that the limit of f of x is equal to L if for every epsilon bigger than 0, there exists a delta bigger than 0 such that for all x in the domain, if 0 is less than the absolute value of x minus p is less than delta, then absolute value of f of x minus f of p is less than epsilon. Nope. That's continuity, Chris. That's continuity. And well, for continuity, right, it's the same definition in that you all already wrote it down. For every epsilon bigger than 0, there exists a delta bigger than 0, such that for all x in the domain, if absolute value of x minus p is less than delta, then absolute value of f of x minus f of p is less than epsilon. Let's make those epsilons cleaner. And we've proven a few things about interactions between the concept of the limit of a function and continuity of that function. If U is a subset of R, a function f from U to R and a point P in U, if P is a limit point of U, then f is continuous at U if and only if the limit as x approaches P of f of x is equal to f of P. If P is an isolated point of U, then f is automatically continuous. So that's just restating stuff from Monday. So today's goal is those three theorems which tell us that all of these concepts, these new concepts, limit points, limits of functions, continuity of functions, they are not new at all. They're all given in terms of sequences. So the point of today is you know lots of stuff about sequences. You know limit laws about sequences. If you want to prove something about a limit of a function, you can get that result by translating everything inside to a sequence. So let's kind of see what he's saying. Let's let U be a subset of R and P be a point in R. Then P is a limit point of U if and only if there exists a sequence xn such that for all n, xn is in U, different from P, and such that xn converges to P. So there's another reason that you might want to call this a limit point. It's literally the limit of a sequence. Sequential continuity. Let U be a subset of R. Let f be defined on U and P be a point in U. Then f is continuous at P if and only if for every sequence of elements of U, such that x of n converges to P, it follows that f of x of n converges to it. And the same thing for limits of functions and limits of sequences. Let's let U be an R. Let's let f be defined on U and let P be a limit point of U. Let's let L be a real number, and then the limit of f of x is equal to L. If and only if for every sequence of elements of U different from P, such that x of n converges to P, it follows that f of x of n converges to L. So every one of these says
you can translate continuity or limits of functions to the world of sequences. How do people feel about these results? People like to see an application before we give a proof?
Yeah.
Let's do an application. Hopefully that's the next thing yeah, that is the next thing I have planned. Good. So I stated those algebraic limit laws. Let's describe how you can prove them by appealing to these theorems that are on the bottom of the previous page. So you've already told me that if f is a constant function, then the limit as x approaches p of f of x is c. The limit of the identity function is that point p where you're taking the limit. Limits add under addition. And all of these are going to have the exact same proof. Yeah, sure. Yeah, probably. In fact, I know that like addition and multiplication are commutative, but let's put them in the right order anyway. F converges to L. L plus M, L minus M, L multiplied by M. That's what happens when I try to like figure out what the statement should say without reading it. So I think I want to just prove this last claim. They all have the same proof. Let's do it. So let's assume that U is a subset of R, P is a limit point of U, and F and G from U to R. Nope, I don't want to assume anything about continuity. Let's assume that the limit as x approaches p of f of x is L, and the limit as x approaches p of g of x is M. In particular, let's assume that means those two limits both exist. Let's also assume that g of x is not equal to 0 for every x in the domain U. And the limit, I fixed this though. I fixed this. No, I fixed it and I uploaded the revision to my Dropbox, but not to the one I printed. So all of these claims are going to pass through the theorem 3. So appealing to theorem 3, let's take a look at theorem 3 and see what it says we have to prove. So theorem 3 says that the limit as x approaches p of f of x is equal to L, if and only if, for every sequence x of n of elements of U different from p, which converge to p, it follows that f of x of n converges to L. So that's what we need to prove then. We need to show that for every sequence x sub n of elements of U different from p, if x sub n converges to p, then f of x sub n divided by g of x sub n converges to L over M. That's what we need to show. Do you see how that's theorem 3 says that that is what needs to be shown to prove this result? Is it not readable?
Can you zoom in a little bit?
Yeah. Yeah, the trouble is like the doc cam's over here, I can't see the screen at all.
Sequences xn of what elements?
Yeah, for every sequence, xn of elements.
Okay.
Elements is just like a really long word. Well, maybe I should just use a shorter word. Points in U minus P. If xn converges to the point P, then f of xn divided by g of xn converges to L divided by n. That's what we should need to prove if we're appealing to theorem 3. So if that's what we need to prove something about every sequence of elements which satisfy some conditions, let's let xn be any sequence of elements of U different from P such that x sub n converges to P. So that's exactly what we should start this proof with if we want to prove that statement in full. Well, tell me, appealing to theorem 3 again, what can you tell me about the limit as n goes to infinity of f of x sub n? Because our theorem 3 is an if and only if, right? So it says that that limit should be the exact same as the limit as x goes to p of f of x. It would be f of p if you wanted it to be like continuous.
Okay.
But we're not trying to prove continuity right now. We're trying to prove a statement about the limit. You don't even know that f of p exists.
Oh,
P
sure.
is by assumption in the domain. And what's the limit as x goes to p of f of x? L. Good. Thank you. I would have written m accidentally. So similarly, what's the limit as n goes to infinity of g of x sub n?
G of x.
It's the same as the limit as x goes to p of g of x. And what is the limit of g of x? So, do we have a limit law for sequences that tells us what the limit as n goes to infinity of f of x sub n divided by g of x sub n must be?
Yeah.
Yeah, it should be L over m or m over L. L over m?
Yeah.
Okay. Wait, have we just shown that for absolutely every sequence of elements of U, different from P, which satisfy that x sub n converges to P, it follows that f of x sub n converges to L over, f of x sub n divided by g of x sub n converges to L over m?
Yes.
Yeah. Hey, so that means that by theorem 3, we can conclude that the limit as x approaches P of f of x divided by g of x equals L. What do people think of this proof? How do people feel about the fact that there aren't any epsilons in it?
It does feel kind of weird.
No, it's not equal to L. Thank you.
Wait, why do we write the same? Oh, like in the bottom, we're just kind of like that one line where you wrote L over M in the fill in the blank. That's just kind of recapping what you did, I guess.
Yeah, so what have we proved? We've proven that for every sequence x sub n of elements of U minus P,
Okay.
such that x sub n converges to P, it follows that that
Oh.
limit is L over M.
Okay.
And by theorem 3, that's equivalent to the thing we actually wanted to show. So here's a way to approach lots of claims about limits of functions or continuity of functions. Translate everything to something about limits of sequences. Now use the fact that you know stuff about limits of sequences. You know a squeeze theorem for limits of sequences. Do you think you could probably use that to prove a squeeze theorem for limits of functions?
Probably.
Yeah. And in fact, that's one of the homeworks, I think. So, of course, like, if you're doing that, there's another, like, secret strategy you could use instead. You could say, well, I know that if I want to use these theorems, I would just do, like, the same proof as I did for sequences. So you could, like, just copy almost verbatim the proof of the squeeze theorem for sequences, but replace some big N's with some deltas. And probably you would get the same proof. Anyhow, let's try to prove some of these. I think there's enough time to my goal is to prove theorem 1 and theorem 2. The proof of theorem 3 is the same as the proof of theorem 2, and it's included in this note package, which is why this note packet is 7 pages long. I don't have the intention of getting to that proof at all. You guys should go and like fill in them blanks just to see that you understood the proof of theorem 2. That's the way the youths talk nowadays, right?
Yeah, totally.
So let's let U be a sub. So let's prove theorem 1. So theorem 1 is the statement about limit points of a set in terms of sequences. So let's let U. So maybe it's worth restating. Well, no. Let's just flip back and look at the theorem. Theorem 1 says, let U be a subset of R and P be a point in R. Then P is a limit point of U, if and only if there exists a sequence of elements, x sub n, such that for every natural number n, xn is an element of U different from P, and such that x sub n converges to P. Let's prove that. And right, there are 2 directions to prove. You need to prove that if the thing is a limit point, then there exists this sequence. And you need to prove that if this sequence exists, then P is a limit point. I guess, do people have any strong feelings about which one they would like to see first?
Let's just do the forward one.
Okay. In the order appearing in the packet.
Yeah.
So let's assume that P is a limit point of U. What does it mean for P to be a limit point of U?
For every epsilon greater than 0, there exists a U in big U such that distance between U and P is between 0 and epsilon. Delta, yeah.
Yeah, I mean, it doesn't matter what letter you use, right? You gave it a correct definition. I'm just going to try to use deltas here in this definition because oftentimes when you're proving, you're using the fact that something is a limit point, it'll be a point in the domain of a function. And like delta compares distances between points in the domains in the other notions. So I'm going to, it's not an important point. So that's what we know. I need to cook up a sequence of elements of the domain U that are different from P, which converge to P. And to do that, I'll start with a sequence of deltas. So let's let delta n be 1 over n. Is that a positive number? Yeah, 1 over n is positive, right? Good. So since P is a limit point of U, and this is positive, there exists something in the domain U. It's U there, but I can call it xn. The name doesn't matter. There exists some xn in U such that 0 is less than absolute value of xn minus P is less than delta n, which is 1 over n. Do you guys see how that follows? And let's maybe even just like see if we can convince ourselves without writing any words that this will be enough to prove the desired result. That first inequality, that 0 is less than, does that mean that xn is probably different from P for every n? Yeah. Do you think you could use this inequality to prove that xn converges to P? That's all you need, right? So that's good. You're convinced now that you can prove the result. Let's prove the result. So we have a sequence. We have to show that the limit of xn is equal to P, and that for every n in the natural numbers, xn is different from P. Yes, thank you. And I went and actually looked through some of the one video that I did upload to YouTube. The paper is basically not visible the whole time. So let's prove this false claim. Let's consider any epsilon bigger than 0. Right, so this isn't the only way you could prove it. You could like use a squeeze theorem approach, but I mean, let's do a quick epsilon n thing. I need to prove that the limit of x sub n is equal to P. So to do that, let's consider any epsilon bigger than 0. We'll let big N be something that we'll figure out when we know what we need. Let's consider any little n bigger than big N, then the absolute value of xn minus P, by assumption, is strictly less than delta n. What is delta n? 1 over little n. And little n is bigger than big N, right? So that's less than 1 over big N. Do you think you could set that equal to epsilon and solve for big N? I think big N is then 1 over epsilon.
so that the limit of xn is indeed equal to p as we needed. That was a really fast epsilon n proof, but I mean, it's like exactly one that you've done before. Okay. Cool. Next, we have to show that for all n in n, xn, well, is in U, but it's different from singleton p. So let's see, by our choice of xn, we certainly see that 0 is less than the absolute value of xn minus p. So xn is not equal to p. What else did we assume about xn when we defined it? What set did it live in?
U.
Moreover, xn is an element of big U. Does that imply that xn is in the set that we want it to be in? Which completes the proof. Let's go the opposite direction now. So let's assume that there exists a sequence xn such that for every natural number n, xn is in U minus p, and such that xn converges to p. We need to show that p is a limit point. That is, we need to show that for every delta bigger than 0, there exists a point u in U such that 0 is less than the absolute value of U minus P is less than delta. That's the statement of limit points again. So that's what we need to show. If you want to prove this statement, well, what's the first line you need?
Consider delta bigger than 0.
Yeah. Let delta be something bigger than 0, because you need to prove something is true for an arbitrary delta that's bigger than 0. Now we'll try to come up with this element of the set by using the only assumption we have. We assume that there exists a sequence that converges to P. So let's see, since xn converges to P, what does the definition of the limit tell us?
Xn minus p is less than epsilon.
Well, I don't know what epsilon is, but I do know what delta is.
Yeah.
And in fact, that's missing some quantifiers, right?
Oh, yeah, quite a few.
For what choices of little n? What are the quantifiers?
There exists a big N such that for every little n bigger than that, big N.
Yeah. So let's consider now any little n bigger than big N. Then the thing that you want to be true is true. Absolute value of xn minus p is less than delta. Which that's like one of the things we need. We need to get a thing that's within a delta neighborhood of the point P, and we have that. Let's try to get the rest. What else do you know about the sequence xn? Yeah, but say no, no. It's always positive. Yeah, in the sense that this thing is always positive. Yeah, because xn is by assumption not equal to p. So by assumption, xn is not equal to p. So absolute value of xn minus p is bigger than 0, and I'll even put the 0 as less than where I actually want it. What else do we know about this sequence? What set do its elements live in? U. Also, by assumption, xn is in U.
So let's see. What then is the element of the set U that satisfies that inequality? What choice of little u should I make? How about x of little n? So we have constructed an element. Let's call it, in fact, let's not even give it that name, little u. Xn, contained in u minus singleton p, such that 0 is less than the absolute value of xn minus p is less than delta. Thus, p is a limit point of u, as we claimed. Did that proof seem okay? So let's make as much headway as we can in the proof of Theorem 2. I know that I'm like just wildly falling behind schedule. That's not so bad. So let's let u be a subset of R. Let's let f be a function defined on u, and let's let p be an element of u. We need to prove f is continuous at p if and only if, for every sequence x sub n of elements of u, if x sub n converges to p, then f of x sub n converges to f. And it's an if and only if, so we have to prove like two things. Let's prove them one at a time. Cool, so let's do it. Let's suppose that f is continuous at p, because that's the thing that we get to assume if we want to make this implication. And we need to now prove something about every sequence of elements of u, which satisfy that x sub n converges to p.
Can you move the paper over a little bit?
Yep. So maybe I'll even give the what do we want to show? We want to show f of x sub n must converge to f of p. That's the thing that we need. And so how are we going to do that? Well, we need to show that for every epsilon bigger than 0, there exists a big N, such that for a little n bigger than big N, absolute value of f of x sub n minus f of p is less than epsilon. That's what we need to prove. Well, let's try to prove it. So let's consider any epsilon bigger than 0. This function f is continuous at p. What does that mean? What does that buy you?
For all epsilon bigger than 0, like delta bigger than 0, such that whenever, or for all x in u, if the absolute value of x minus p is less than delta, then absolute value of f x minus f p is less than epsilon.
So there's like the epsilon delta definition of continuity being used. And I left out the for every epsilon bigger than 0 because I've already declared epsilon. That's right. This is the epsilon I want to use. But wait. That delta, that delta that we got there is bigger than 0, and xn converges to p. So we see then that xn converges to p, that's a positive number. We see that there exists some big N, so that for every little n bigger than big N, absolute value of xn minus p is less than delta. Right, so that's just like putting the two assumptions together, listing the two assumptions, the assumption of continuity and the assumption of the limit. Let's play the game now. Let's consider any little n bigger than this particular choice of big N, that big N. So what does item 2 tell us if little n happens to be bigger than big N?
Xn minus p is less than delta.
Absolute value of xn minus p is less than delta. But if xn minus p is less than delta, then what does item 1 tell us?
F of xn minus f of p is less than epsilon?
Yeah. F of xn minus f of p is less than epsilon. So let's just see what happened here. Did I start by considering any epsilon bigger than 0? Did I do some jiggery pokery and come up with a choice of big N? Do I then consider an arbitrary little n bigger than big N?
And then I showed that the absolute value of f of x of n minus f of p is less than epsilon. Okay, that's exactly the statement of the limit of a sequence. Thus, f of x sub n does indeed converge to f of p. Since xn was absolutely any sequence of elements of u converging to p, we get the result that we needed. And, not that the opposite direction is super difficult, but I can't do it in 5 seconds. So, I think in celebration of I've used up all of my time, I'll go ahead and say, people have any questions they want to ask about?
You on the homework later.
Huh?
There's a couple homework questions I have, but that's probably all coming later because that take a while to talk about it.
Okay, cool. I'm going to remember to hit stop recording.